Okay, I was requested by one of my students to put up another video regarding neutralization reactions, specifically ones that involved pH as opposed to molarity, for giving you a bit more information about the problem. So I've got two problems I'm going to do, one a bit more straightforward and one a bit more convoluted towards that story type problem that tends to show up on my test. So this problem involves mixing an acid and a base together, as you would expect in a neutralization reaction. So we're mixing sulfuric acid and sodium hydroxide. 350 mils of a pH 4.2 sulfuric acid solution with a 2.5 molar sodium hydroxide, and they're asking me for the volume. And I didn't say in this problem, again, I apologize since I just make these up, but we're assuming we're neutralizing here. What is the necessary volume of sodium hydroxide to neutralize the acid? Apologies. Anyway, sulfuric acid is H2SO4, sodium hydroxide, so let's see, double replacement, that's going to need a 2, and our water, balance, yay! So if you remember, pH, whenever you P something, you're taking the negative log of it. So pH is the negative log of the hydrogen concentration. If you think about neutralization reactions, the entire point is to try to get every H plus and OH minus. That's how we neutralize something, is to make equal amounts of H plus and OH minus floating around in our solution. So this number right here is what's going to tell me my concentration of H+. So it's going to do that solution stoic-ish looking thing for me. So to find out the concentration of H+, remember it's actually present in my solution as hydronium, I need to do 10 to the negative pH. That's my formula. So we're going to do 10 to the negative 4.2. 10 to the negative 4.2 gives me 6.3096 times 10 to the negative fifth. And this is a concentration. So I don't have to worry about the fact that I get 2 hydrogens per sulfuric acid. This did all of that for me. So now that I have the molarity, I can use my volume here to figure out just how many moles of that hydrogen are floating around in this solution. So I have 350 milliliters, that's about 0.35 liters. Liters cancel, and I'm left with just moles. 2.208 roughly times 10 to the negative third moles of hydrogen ion floating around. Since I have 2.2 times 10 to the negative fifth moles of hydrogen floating around, that means I'm going to need 2.08 times 10 to the negative fifth excuse me, moles of hydroxide to neutralize that. But I can't pull hydroxide off the shelf. In this problem, my hydroxide came from the sodium hydroxide, our 2.5 molar sodium hydroxide, in fact. So, sodium hydroxide has 1 hydroxide per sodium hydroxide molecule. My solution is 2.5 moles per liter. And you could stop here, or you could go all the way to milliliters. I'll go ahead and stop here for now. Divided by 8.83 times 10 to the negative sixth liters of our 2.5 molar sodium hydroxide. That is how much I will need to neutralize our pH 4.2 acid. That's that many milliliters. So that's one example for you of a neutralization problem involving the pH. Here's the second one. Let's see if we can get this one done before my time runs out. So this one is a bit more of a story, and it's partially true. Since I make these up off the top of my head, I'm not really sure if the numbers are right, but it is true that blood chemistry is dependent on pH. So this one says that blood chemistry is important to the efficacy of various medications. Cancer treatments work best if the blood is slightly basic, pH of 7.8 or so. I'm not even going to worry about that 7 or that or so that looks important. If a patient has a blood pH of 6.9, how much of the 0.001 molar sodium hydroxide solution must be administered to create the necessary blood pH? So we are looking for volume in this problem, ultimately, a volume of this potassium hydroxide solution. But they gave me 2 pHs. I'm wanting to change my pH. So this time, I'm not going to neutral. I don't want to know how much it takes to neutralize my acid. Instead, I'm wanting to overshoot, to go to 7.8. So, if I'm starting out at 6.8, let's figure out what concentration of H plus we have here. So if you remember, to calculate, our hydronium concentration, that H plus, that's an H plus with a water, we need to do 10 to the negative pH, so that's 10 to the negative 6.9. 10 to the negative 6.9 gives me 1.259 times 10 to the negative 7th molar H plus. So this is where I'm starting. My pH of 7.8 is where I want to end. So let's see how much hydronium it takes for that. So 10 to the negative 7.8 gives us 1.585 times 10 to the negative 8th molar hydronium. So notice to do this, my amount of hydronium has to go down, and the only way we can do that is by binding up my H plus with the OH from my base here. So that means I need to figure out how much H plus do I need to get rid of? How much do I need to lose? So I'm going to subtract these two numbers that I've gotten. Oops. Excuse me. So this is how much H plus I need to get rid of. And again, the only way to get rid of H plus is to bind it up with OH. So if I need to get rid of this much H plus, that means I need to get that much OH. Now we're back into that typical neutralization territory. This is a molarity, so this is moles per liter, but now we're looking at hydroxide instead. My hydroxide is coming from my potassium hydroxide, which is a 1:1 ratio of my ions. And let's see here. I have a point. Oh my goodness, you know what I forgot? Look at that. I forgot to tell you the volume of blood. You need to know just how much of this acid do you have. That would be important, wouldn't it? Because here was my mistake right here. I should not have stopped in molarities. I should have stopped in moles. What do you know? Well, let's go back and fix that. I'm glad I caught that mistake. Body usually holds what? 8 to 12 pints of blood, so we'll say it's a small person, 8 liters. I apologize. Look at that mistake. 1.259 times 10 to the negative 7 times 8. Whoops. Helps if I put the right numbers in my calculator. So my process is going to be the same. I just got to change some numbers. And the whole reason, just as a side note, the whole reason I knew I had done something wrong was because everything was going to cancel down here in my setup. Moles and moles, moles and moles, liters and liters. So that was my clue that something was amiss. I got to get to moles of my ion, not molarity, you ding-dong. So again, we're saying that this is an 8 liters of blood in the human body. So, still true, notice, hydroxide or hydrogen went down. Okay, that looks much better. Now then, as I was saying, since we have this much H plus that I want to get rid of, the only way I can do that is by binding up that much H plus with that much OH. My OH is coming from the potassium hydroxide. And my potassium hydroxide had a molarity, according to my problem, of 0.001 moles. I'm going to go ahead and go to milliliters because I have a hunch this is going to be a very small number. So 0.88 milliliters of our 0.001 molar potassium hydroxide. Sorry for that mistake in there, but I hope it just goes to show you how as soon as something seems off, go back and double check your work. Use your units to track yourself. Your units should always cancel when they're catty-corner from one another. If they don't, that tells you you did something wrong, and in this case, all of my units canceled, so I knew something was amiss, so that led me to go back and fix my mistake. Well, I hope this has shown you a couple of different ways that acid-base problems can be presented outside of the stereotypical black and white problems. If you have any questions, leave them in the comment box below, and I'll get back to them as soon as I can. Take care.